Well, this might be hot. It's the Heaviside approach to the same type of problem attributed to Oliver Heaviside. He thought of this. If we have a fraction of the form P of S over Q of S, the fraction is proper. That means the degree of the numerator is less than the degree of the denominator. And in lowest terms, and the denominator factors into n distinct linear factors, s minus c1, s minus c2, s minus dot 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 f to s minus c sub n, then the first step in the partial decomposition is to write P of S over Q of S is just like we did before. This fraction, dot 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 out to this fraction, plus some remainder where Rs is a collection of terms not involving S minus Ci, if there are any. And so Heaviside Formula 1 says the AI, every one of those is P of Ci, so whatever this is, P of that over Q prime of whatever that is. This P and this Q. In our problem example 2 above, see, this one, we wanted to find this inverse transform. This is the P of S. The Q of S would have been all this multiplied out. So in order to find the Q of S, we'd have to multiply that out, and that's what it is multiplied out. But then we'd also have to find, there it is multiplied out, including the 2s there. And then we'd also have to find its derivative, and that's pretty easy. Derivative of polynomial, what gets easier than that? So A, in this thing we did up here, the A is P of 2 over Q prime of 2. Well, P of 2 is 5. Q prime of 2 is 4 times 8 minus 6 times 4 minus 2 times 2 plus 2. And so there's all that worked out, and that turns out to be 5, 6. Well, that's what we got when we did it before, but this seemed a lot easier to me. Especially we didn't even have to do that matrix thing. And B would be P of 0 over Q prime of 0. Remember why it's that? Because up here our B was over S, so that's S minus 0. So we find P of 0, which is 1. Put in 0 for that, we get 1. Q prime of 0, we get 2, so 1/2. And guess what? That was the first thing we found up here. B was 1/2, right? And so on and so forth. C is P of -1 over Q prime of -1. Well, P of -1 is 2, because -1 squared is still 1. And Q prime of -1 is -4 minus 6x minus 10 plus 4. Minus 10 plus 4 would be -6. So it's 2 over -6, so -1/3. And D is P of 1 over Q prime of 1. Well, that would be 2 over Q prime of 1 would be 4 minus 6 minus 2 plus 2. So 2 over -2, and that's -1. And if you recall, that was the value we got for D, C. A was 5, 6, B was 1/2. And so that seems a little bit easier to use a Heaviside approach with linear functions like that. Now, there's another formula for the Heaviside approach, which might or might not be useful, but the idea is there should be a nicer way to do this if we have repeated factors, like if S minus C is a repeated factor. The partial fraction decomposition would say we have to have S minus C to all powers up to however many times it occurs. Like, you know, if Q has a root of C of multiplicity R, then S minus C to the R is the highest power of S minus C that we need in the denominator, but we need all positive integer powers up to that R, plus the R of S, where S is some other stuff not involving S minus C. But that's kind of nice, because if we let phi of S be our S minus C to the R times P of S over Q of S, then backwards, it's kind of backwards, A sub R is phi of C, A sub R minus 1. See, I'm giving you these coefficients backwards. I'm giving you this one first. So it's just phi of C, A sub r minus 1 is phi prime c over 1 factorial. A sub r minus 2 is phi 2 primes over of c over 2 factorial, and etc. and so on. So, and a1 is finally the r plus first derivative of phi evaluated at c. So the r plus first derivative of this evaluated at c over r minus 1 factorial. Now here's an example of Heaviside Formula 2. Suppose we wanted to get a partial fraction decomposition of something like this. And we say, well, we got s minus 4 cubed, so we need s minus 4 squared, and s minus 4 cubed. And so our phi of s is s minus 4 cubed times s squared plus 2 over s minus 4 cubed. So it's just s squared minus 2. So a3, that's the highest one, is just phi of 4. Well, phi of 4 is 4 squared plus 2, which is 18. A2 is phi prime of 4, but phi prime of 4 would be 2 times 4, which is 8 over 1 factorial. See, the factorials start coming into play on this one. And that would just be 8. And finally, a1, which is the last one we need, is double second derivative at 4, so that would be 2s, and then another derivative, oh, it's just going to be 2 over 2 factorial, which is 1. So here is the partial fraction decomposition. This turns out to be, I didn't actually write that, so here it is, p of s over q of s, s squared plus 2 over s minus 4 cubed is 1 over s minus 4, plus 8 over s minus 4 squared, plus 18 over s minus 4 cubed.